For thousands of years, we've relied on a very specific method to guarantee mathematical truth: humans writing equations on a physical surface and other humans checking our work. But today, modern mathematical proofs now span across hundreds of dense pages. At that scale, reviewers miss dropped variables, subtle logical leaps, and simple human errors. The manual checking system breaks down. To solve this, researchers developed the Interactive Theorem Prover, or ITP. An ITP is a specialized software environment that collaborates with a mathematician to formalize and check logic step by step. Lean 4 is the most modern version of this tool. It operates as a fully functional, general-purpose programming language that also happens to have a strict mathematical proof checker built directly into it. We have reached a point where the underlying equations describing our world are simply too massive for a human brain to verify alone. We need machines to guarantee the math is right. Curious, but a strict programming language is designed to manage memory and execute commands, not ponder abstract mathematical concepts. How do you force a computer to understand logic? The answer is the Curry-Howard isomorphism. This is a computer science principle stating that mathematical propositions and software programs share the exact same underlying structure. Under this principle, a mathematical statement, like A implies B, is treated as an empty data type. Its proof is just a standard computer function written to output that specific type. If the code compiles without errors, the proof is objectively true. Proving a complex theorem is now mechanically identical to writing bug-free software. Let's look at how a mathematician actually works inside Lean. The interface is split into two halves: the human text editor on the left and the machine's active feedback state on the right. This interface shows the system's goal state. The goal is the specific, unyielding mathematical target, like proving that 0 plus n equals n, that the software demands you solve before it will compile. Writing raw computer functions for every tiny step of a proof would take years, so Lean uses tactics. Tactics are shorthand, human-readable commands that automatically generate the complex underlying code for you. This screen shows the user applying an induction tactic. It works backwards, slicing the main goal into two simpler subgoals. The system is dynamic. As you type a tactic on the left, the goal state on the right updates instantly. The mathematician gets to think in high-level logical steps, while the tactics quietly write the highly structured, foundational code the computer needs. The mathematician repeats this interactive process, chipping away at the subgoals until the target is reduced to an absolute, self-evident truth, like 2 equals 2. At this point, those shorthand tactics have secretly constructed an enormous, dense block of raw mathematical code in the background. That massive block of code is sent to the final judge, the kernel. This tiny, isolated piece of architecture acts as the ultimate authority. It ignores your tactics, exclusively checking the final code block to ensure the data types match perfectly. Because the kernel is so small and isolated, the chances of a software bug accidentally approving a false theorem are virtually zero. Because Lean separates the user-friendly tactics from that strict, isolated kernel, the system scales to handle incredibly complex problems without breaking down. This architecture enabled the creation of MATLib. MATLib is a massive, open-source library where thousands of researchers are collaboratively digitizing human mathematics into executable code. This digitized math provides an ideal environment for training artificial intelligence. Because Lean instantly tells you if a proof compiles or fails, an AI gets immediate, objective feedback on its work. AI models use Lean 4 to run millions of trial and error attempts, learning the rules of logic to verify completely new mathematical pathways. We are moving away from the solitary mathematician, hoping they didn't make a mistake on a physical chalkboard, toward a global, machine-checked network of objective truth. By translating logic into compiled code, we ensure the complex equations governing quantum mechanics to computer science are permanently, provably correct.